Hello, my name is Yasir. Today I will try to solve a stochastic differential equation. So for that, I will share the screen. So I will use a method to solve a stochastic differential equation. The method I will use that's Euler Maruyama method. And first I write the equation. I will bring the deterministic model. The equation without stochastic term, I will bring that, and then I add a Brownian motion term in it. Suppose that this is the equation. So I add a stochastic term. So it can be written as y prime is equal to y plus x ex, and then the stochastic term. The stochastic term, the Brownian motion term, I will add in this way that sigma is the coefficient, and then y, the dependent variable, and then dw, or it's a dw, the Brownian motion term. Now I will use the Euler-Maruyama method. For doing that, for applying that, it can be written as y n plus 1 minus yn divided by the step size. Suppose that that's h, I use h, or delta t. And then, so that's approximation for the derivative. And now the remaining term, dependent term will be evaluated at the nth grid point or nth time level. So here this is xcx, and then sigma. Using Euler-Maruyama method, this term can be written as sigma yn, and then this is delta w. That's the integral of. So the integral of dw is just a delta w over tn to tn plus. So that's the integral. And delta w is further approximated to normal distribution with zero mean, and with variance of delta t, or standard deviation of square root of delta t. So that's approximated as a normal distribution. So now I will make a code in Matlab. So first I start with CLC. And then starting point suppose at 0 of the domain, and end point of the domain is maybe 1, and the number of points are 100. T is space T naught, then T1, and number of points then, and dt is T1 minus T naught over n minus 1. And you suppose that y, okay, y is the dependent variable, so y can be one column. Initial condition suppose that is 1. And now I use the loop for n is equal to 1 to ln. So this equation I have. So this equation can be written in the form yn plus 1 is equal to yn plus h into yn plus x, dx, and then plus sigma y delta z. So yeah, this is the x is the independent variable, so I can use here as a t. So x can be replaced with t. So what I will use the last equation. So it's a y n plus 1 is equal to yn n plus dt instead of h. I use dt and then yn plus it's a tn. It's a yeah, tn multiplied by t to the power tn, then plus sigma yn plus sigma yn, and that's a normal, that's a Brownian term. So first I will use uh, make a distribution, normal distribution. I will use Matlab command and then with a zero mean and square root of dt as a standard deviation. Then I will use this thing here. So uh, we must use the random command. So dw is the random, it's pt. So I will use pw here. So then I end up and then like Lord and y. Now if I run this code, oh sigma is suppose that sigma is 0.1. So we run the code. Yeah, this is the solution. So if I increase the sigma, if I increase this coefficient, so the solution would be right there. So that was the Euler Maruyama method. So even I can use one more loop of it. So I can use an extra loop for j is equal to 1 to 5, and then this will be n here, and then what I will do here. So I can plot each one. So in one figure, all the solution will be plotted. So these are the five. So one figure. So even I can find their average to for finding average value. What I you know. And, uh, yeah, fine. So I will try to find the average of everything. So the average would be I will write every solution that would be S one plus S2 plus divided by 5. Where I use that average. Yeah, that's very fine. So this is the average solution. So this is the average of all the solutions. So that was here one more thing is that here I can use the updated means that I use yn plus tn. So it can because the solution is founding at because solution will be found at n plus one step size. But here I use the n step size, so I can change it. Plus- Not here, not with y, but with tn. So not right under the so this is the thing. So this is the solution of stochastic differential equation. Y and this with you.